semiconductors, right? So first we are going to start with conductors. What is meant by conductors? So the conductors, we have a number of free electrons even at 0 degree Celsius. So for example, I suppose consider a conductor. We have it has free electrons. Then if you are applying some external potential, the electrons easily can move from one point to another point. Because of the motion of the electron, there will be some finite current. So in the case of conductor, we have a number of free electrons. So the conductivity of the conductor is very much larger than the resistivity is very much lesser. So sorry, resistivity is less and the conductivity is larger because we have initially free electrons. Then what is insulator? So I have an insulator. Initially there is no free electrons. No free electrons for the conduction process. So here the conductivity is very much lower, resistivity is very much larger. In case if there is no free electrons, there is no current because of the applied external potential. So we have two cases. One is without, we have free electrons. In this case, we have a number of free electrons. So what is meant by semiconductors? My semiconductor is also initially as an insulator. Initially, in semiconductor also, there is no free electrons. So for semiconductors, initially there is no free electrons. So here also conductivity is less, resistivity is larger. So initially there is no free electrons. So what is the difference between the insulator and the conductor and the semiconductors? So here also no free electrons. Here also no free electrons. Why we call this as semiconductors? So here, if you are supplying some amount of energy to the system, the electrons will coming out from the valence band to the conduction process. But in the case of insulators, the amount of energy required is very much larger than the semiconductors. So if I apply some energy to the system, the electron gain that energy from the outside, and then it will become a free electron. Then this will conduct the current. So semiconductors also initially as an insulator. So we are going to study about this semiconductors. We have a variety of semiconductors. So in this chapter we are going to study about majority silicon and germanium based semiconductors, right? So for the conductor we have a Ohm's law. What is Ohm's law? Ohm's law is nothing but my V is directly proportional to I. So my applied potential for the conductor, sorry, in the case of for the conductors, we have a Ohm's law. What is Ohm's law? V is directly proportional to I. So if I increase the potential, the current also gets increases. So it gets increases linearly. If I increase my potential, my current also gets increases. But in the case of semiconductors, if you are giving some potential, this amount of energy is spent to remove the electron from the valence to the conduction process. So initially there is no increase in the current. So if you plot a graph between the potential versus current for the semiconductors. So initially we are giving some energy to the system. This energy is spent to remove the electron from the valence shell to the conduction process. Initially, if I am increasing, nothing is happening. If I increase this, then only the current will get increases. So initially, there is no free electrons. This amount of energy is spent to remove the electron. Once the electron is removed from the valence band for the conduction process, then the current will increase drastically. Sir, why the current increase drastically? So now we are going to the current electricity. So what is meant by relaxation time? So the relaxation time means it's an average time interval between two successive collision. So in the case of conductivity, we have a conductivity which is directly proportional to the relaxation time. This tau stands for relaxation time. So in the case of semiconductors, there is no free electrons. We are generating one or two free electrons. Because we have a less number of free electrons, the collision probability will be less. If the collision probability will be less, the relaxation time will be more, because the average time between two successive collisions will be very much larger. So this is larger, my conductivity also larger, so the current will increase drastically. But which will not obey your Ohm's law. So the material which will not obey your Ohm's law, so those kind of material is called non-ohmic materials. So that's why the semiconductors are called non-ohmic materials. So semiconductors are called non-ohmic materials. Okay. So we are going to study about the semiconductors. Sir, in this case, I am not able to use my Ohm's law. Then we need some other theory to understand the semiconducting material. What theory? It's called energy band theory. So now I explain the energy band theory. So semiconductors are called non-ohmic material. So energy band theory. So I can simply write, in case I am supposed to consider the valence shell. So I have the outermost orbit. Okay. So the center we have a nucleus. I am going to consider electrons in the outermost orbit. Listen. So I am going to consider electron E1 and electron E2, and I have electron E3. So each electron having different energy levels. Okay. So each electron having the different energy levels. So what I'm going to do here, I'm going to plot a graph versus graph for the energy of the each electron. Listen carefully. So this is the energy So first, the energy of the first electron is say some value. This is energy of the first electron. So I have an electron 2, it may have the different energy. So this is the energy of the second electron. Then I may have the another electron 3, this energy may be here, E3. So this is the set of energy levels possessed by the electrons in the valence band or valence C. So the set of energy levels possessed by the valence electrons is called valence band. Band means is a set of energy levels like your frequency. Okay. So this is the set of energy levels. This looks like a band. So okay. So this is called the energy of the valence band. Okay. E valence, energy of the valence band. Sir, if you want to remove the electron from the valence to free process, so the amount of energy required. So now we are coming to the dual nature. What is the work function? It's the amount of energy required to remove the electron from the its valency or metal surface. It's called your work function. So the amount of energy required, E, G. So if I give this is the minimum amount of energy required to eject the electron from the valence to the conduction process. It's called free electrons. So the amount of energy required here, say, so this is my amount of energy required. For example, this electron may need some 2 joules or 2 electron volt or 3 electron volt or 1.5, whatever the number. Okay, so the amount of energy required to eject the electron from the here to the free process. This means it's called conduction process. It's called the energy gap. Okay. So if I apply this energy, because of this applied energy, what's happening? This electron is removed from here to for the free. It will become a conduction electron. So the energy possessed by the electron, which means now this is removed. So we have a free electrons. So this is called a free electrons. So energy possessed by this electron will be here. The energy possessed by the second electron will be here. the energy possessed by the third electron will be here. So this looks like a band. So it's a set of energy levels possessed by the conduction electrons or free electrons, which call the conduction band. This is called valence band. So this is called band theory. So this is the energy possessed by the valence electrons. So this is the energy possessed by the free electrons or conduction electrons. So this is the amount of energy required to bring the electrons from valency to the conduction process. So next, how can we differentiate conductor, insulator, and semiconductors? So first I'm going to start with the conductor. For the conductors, this is my energy. So this is the energy of the valency, and this is the energy of the conduction electrons. Here my EG is nearly 0 because initially we have a free electrons. If I have initially free electrons, there is no amount of energy required from the outside. So there is a overlap between your valence band and your conduction band. So your electrons, there is no amount of energy required. There is no gap between the two bands. So now I am going to plot this for insulators. Energy and the insulators. So this is my E, V, E, C. So the energy required to eject the electron from the valency is greater than 3 electron volt. So the amount of energy required, the amount of energy we are giving to the system to remove the electrons from valence to the conduction process is greater than 3 electron volt. Then it's said to be insulator. So this is for the insulator. Sir, then what's happening if you are giving more than 3 electron volt? So if you are applying more than this amount of this amount of energy, the dimension, the characteristics of the material will change. So that's why we are not prefer more than 3 electron volt for the semiconductor, for the conduction process. So in the case of semiconductors, I have energy. This is EV. This is EG. Okay. So here the energy gap EG, which is less than 3 electron volts. So this is how they characterize, they differentiate. So the energy required, if my energy gap is 0, then it's insulator. The energy gap is less than 3 electron volt, then it should be semiconductors. This is greater than 3 electron volt, then it's specified as an insulator. Okay, so this is very important for the exam point of view. So okay, next I am going to explain the intrinsic semiconductors. So the majority of the case for the semiconductors we are going to use only silicon or germanium. So why they prefer silicon and germanium? The availability, the abundance. So the availability of the material, the raw material from the earth, it's germanium and silicon is larger. So that's why we choose silicon and germanium for the semiconductors. So first I'm going to start with intrinsic semiconductors. intrinsic semiconductors. It's nothing but pure semiconductors. Okay, first I'm going to start with our example. We have a silicon and germanium. For silicon also we have a valency of 4. For germanium also we have a valency of 4. Right? So for silicon also we have a 4th valency, and germanium also we have a 4th valency. Okay? So first we should know what is meant by a covalent bond. So the covalent bond is nothing but the sharing of electrons between the two nearest neighbors. Okay, so if I consider chlorine is always form a bond with, it's always sharing an electron with the nearest neighbor. For example, you cannot find chlorine separately. Cl you cannot find. You can say Cl2 or HCl or NaCl, something like this. Okay, so first I'm going to start with silicon. I'm going to start with the silicon, right? So we have silicon. Silicon we have a 4 valency. So this is sharing 1 electron with this nearest neighbor, and this is share 1 electron with the nearest neighbor of the same material, silicon. This is sharing 1 electron with the nearest neighbor, sharing 1 electron with the nearest neighbors. So there are 2 electrons there. This is a covalent bond between this is one silicon, this is another silicon. So 1 electron sharing from here, 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 1 electron sharing from here. So this is how there's a sharing of electrons between the silicon, right? So next is there is no free electrons initially. That is why we are going to give some amount of energy to the system. So if I suppose to give some energy, it's nothing but my thermal energy. I'm going to heat. Okay, I'm going to give some thermal energy. What's happening? The electrons in the valency is gain some energy from the thermal energy, and it become a free electrons. So these electrons will come here because of the this is nothing but your thermally generated electrons. The electrons is move from here to here. So this is called free electrons. This is called thermally generated electrons. So we have to give some amount of energy to remove this electron. Sir, if I remove the electron from the particular point, what's happening? There's a space, there's a vacancy. So this vacancy, it's positively charged because I'm removing the negative charge. If I remove the negative charge, there will be automatically a positive charge, right? Then automatically there is a positive charge. Okay, this vacancy is called holes. So from here onwards, if I use circle, it's called holes. If I use dot, it stands for electrons. So holes are the positively charged and the electrons are the negatively charged, right? So right. Okay, so because of motion of this electron, there will be some finite current. The current generated by the motion of this free electron is called electron current. Electron current, right? EC, EE, okay, IE, electron current. Okay, so now we have a number of electrons. The number of electrons is going to be N E. This means number of electrons. Okay, then there will be a drift process. So this is my vacancy, this is my positively charged vacancy. So this electron which will move from here to here. So this occupy this space. So this space will be empty. Then this electron will move from here to here, and then this space is occupied and this space will be empty. See, after sometimes I am looking this, so there is a shifting of a hole from here to here. Actually, there is no shifting of your hole. There is a shifting of your electrons from one point to another point. But the apparent the apparent is the hole is shifted from one point to another point. Actually, the holes are not shifting. The electrons are shifting from one point to another point. If the electrons are shifting from one point to another point, because of this, it looks like your hole is moving from here to here. So some minimum amount of current will be generated because of the drift of the electron from this point to this point. So I can simply write the current produced by the motion of the electron from here to here. Actually, this is the motion of the electron. What we are considering for the simplicity, there is a shift of the hole from here to here. So the current generated by this process is called hole current. Hole current. So the number of electrons, number of holes in this case is going to be NH. Is called number of holes. Okay. So we have something like this. So one current is produced by the motion of the electron. One current is produced by the motion of the hole. So this is called electron current. This is called hole current. If I say the total current I equals to IE plus IH. Okay, IE plus IH. But this is similar. I mean, total current is nearly equals to IE because my IE is very much greater than IH because the electron current is because of the motion of the free electrons. This is just a drift of the free electrons from one point to another point. So then I'm going to write the number of intrinsic carriers here. So I can simply write my number of intrinsic carriers here Ni equals to Ne, Ni square equals to Ne into NH. This is my number of holes and number of electrons. Okay. So in the most of the case, my number of electrons that is nearly equals to number of holes because each free electrons which is generated one holes. So each free electrons which is generated one holes means so there will be vacancy for each free electrons. So the number of electrons equals to number of holes. If I apply this condition here, then I can simply write Ni square equals to Ne square. Okay. So this is very important formula for the exam point of view. So Ni square equals to Ne into NH. Ne is nothing but number of electrons. NH is nothing but number of holes. This is the number of intrinsic carriers. Right? Okay, sir. Next step. So now I'm going to plot the energy level graph. So I have an energy level graph here. Energy versus this. Okay. Here we have a conduction valency. Okay. So at 0 Kelvin, so this is for at T equal to 0 Kelvin. Okay. We have 4 electrons in the valency. There is no electrons in the conduction band or conduction process. So there is no electrons for the 0 Kelvin. Right? Next, after applying this heat energy, there will be creation of electrons from here. So this is my EC, EV. So this is T is greater than 0 Kelvin. When T is greater than 0 Kelvin, for example, in this case, 2 electrons is moves from valence band to conduction band, then there will be 2 vacancy. So this is one vacancy, this is one vacancy. This is hole and this is hole. When 2 electrons moves from here to here, which will leave 2 holes, right? This is the demerit of the intrinsic semiconductors. So why this is demerits? Simple, because there is at 0 Kelvin there is no free electrons, there is no conduction process. At T is greater than 0 Kelvin, what's happening? There's a creation of free electrons. So every time I cannot provide energy to the system. Yet if I provide energy to the system every time, the system will, the material will get damaged. So this is the major problem in the intrinsic semiconductors, because every time I cannot heat the system then start using. I cannot heat the system every time the material gets damaged. How to overcome this problem? To overcome this problem, we have another kind of material. It's called extrinsic semiconductors. Okay, now I'll explain. Okay. Okay, ma'am. So extrinsic semiconductors. The extrinsic semiconductor is nothing bad. We are going to add some impurity to the pure semiconductors. So, what is mean by impurities? Okay, impurity is also another element we are going to add to the silicon or germanium. So, sir, first we are going to start with N-type semiconductors. N-type semiconductors. So, what is meant by N-type semiconductors? What I told you, extrinsic semiconductor means we are going to add some impurity to the system. If you are adding some impurity to the system, we should not add large quantity. We are going to add only small amount of energy to the small amount of impurity to the system. Sir, what is this small amount of energy? What is small amount of material? It's called 1 ppm. It's called parts per million amount of impurity we have to add to the system. So we should not add more amount of impurity. If you are adding more amount of impurity, what's happening? The number of free electrons will be larger. If the number of free electrons will be larger, what's happening? Then there will be a collision probability will get increases. If the collision probability gets increases, what's happening? The relaxation time will be reduced. If the relaxation time will reduce, the conductivity gets reduced. Okay. So we are going to add the impurity only for the 1 parts per million. Okay, sir. What is N-type semiconductors? The impurity type is could be the pentavalent impurity. Pentavalent means the valency of the electron, the valency of this element is going to be 5. So the valency is 5. I'm going to take arsenic, best example, the arsenic and antimony and phosphorus. Okay, arsenic, antimony. So these two are the best examples. So we have a 5 electrons in the valence, right? So first I'm going to start with, so I have arsenic in the middle plus 5, which means it has 5 electrons in the valence shell, right? So this is my silicon. We have plus 4 here. This is silicon plus 4. This is silicon plus 4. This is silicon plus 4. So we have a bond, covalent bond between the arsenic or antimony. It's going to be, it's a pentavalent element which is going to be form a covalent bond between the silicon. So that's a sharing of electrons from one from impurity, one from silicon. So here again one from impurity, one from semiconductor silicon, one from impurity, one from here. Again one from this and one from this. So out of 5 valence electrons, 4 electrons are shared. The 4 electrons are shared. If the 4 electrons are shared, 1 electron is free from the impurity, because since it's a pentavalent element, the 4 electrons shared with the nearest neighbors. Sir, this free electrons is initially at rest. So this impurity which will donate one electron to the system, which will donate one electron for the process. Sir, I can simply write here. I have a positive plus here. So this is your impurity. So this is called donor core. Donor core means which will donate one electron to the system. It's called donor core. So initially this is also not moving. So we have to provide some amount of energy to the system. So if I plot a graph here, energy EV EC, right? Here, the energy of this donor, the minimum amount of energy we have to give to the system. Okay, not like your previous case. In the previous case, we have to provide larger amount. In this case, we are going to provide only very small amount of energy to the system. So the amount of energy required to move this electron to continue the process is we call the energy of the donor core. ED means the energy of the donor core. It's a minimum amount of energy required. So this energy gap is approximately 0.01 electron volt. I think I forgot the value. Approximately 0.01 electron volts. It's a very minimum amount of energy required to move this electron. Listen carefully. So the amount of energy required is very minimal because to move an electron from here to here is tough. To move an electron from here to here is easy. So the energy of the donor core stands for ED. Okay, in this case, we have a number of electrons is very much greater than number of holes. Okay, in this case, because each impurity which will provide one electron. So each impurity which will provide one electron means we have a number of electrons is larger. If the number of electrons is larger, then this electron is larger. Electron is the negatively charged particle. If it is electrically charged particle, that's why it's called N-type semiconductors. So N-type semiconductor means the negatively charged N-type semiconductor, negatively charged electrons dominating here, right? Then, if you have any doubt, just write in the comment section. I'll answer in the next class. Okay. So next we are going to discuss about the p-type semiconductors or positive type semiconductors. So in the positive type semiconductors, nothing but in this case we add the impurity of pentavalent impurity. It's called 5 electrons we have, right? So in the case of p-type semiconductors, it's a trivalent impurity. Okay, next we will discuss. So I'll read in this graph for the comparison. So this is called p-type semiconductors. So for p-type semiconductors, we need a trivalent example on the aluminum and boron. Aluminum and boron. So it's the valency of this impurity is 3, right? So in this case, I have a plus 3. We have silicon plus 4. Plus 4 means we have 4 valency. Here we have a 3 valency in the case of aluminum as well as the boron. Okay, right? So it will form a covalent bond with this and this. one electron from the impurity, one electron from the semiconductor. One electron from the impurity, one electron from the silicon. Here one electron from the impurity and one electron from the, actually there should be a vacancy, right? Because my impurity having only 3 valency. If my impurity having only 3 valency, so there is no electron to sharing with this silicon. So this is, for example, if I consider this my aluminum or boron, so that it has 3 electrons. One is shared with this silicon, one is shared with this electron, one is shared with this silicon. So there is no electron to share with this silicon. So there will be a vacancy. So here each impurity which will provide one electron, one holes for the process. So in this case, my holes is very much greater than number of electrons. Clear? My hole is very much greater than number of electrons because each impurity which will provide one hole. Then if I say this is minus, which will accept electron from here. Okay, so this is plus. So these are called the plus, these plus signs stand for the silicon, this minus sign stands for the impurity. This is called the acceptor core. This is nothing but each acceptor, each impurity which will accept one electron from the silicon. Okay, sir. So what is the process? So one electron, because if you want to move electron from here to here, we have to provide some amount of energy to the system. So one electron moves from here to here. So this vacancy is filled. If this vacancy is filled, this will be vacancy. So this is filled by these electrons. So here this will be vacancy. So there will be a continuous motion of the electron for this hole. So there will be a creation of some amount of current. Okay. So the amount of energy given to the system is also minimal. So if I plot the same graph here, this is for N type and this is for P type. Here each donor core which will provide one electron to the system for the conduction process here. But in this case, each acceptor core which will accept one electron from the system or semiconductors. So the energy of the acceptor core is nearly somewhere EA. The energy of the acceptor core is nearly somewhere here. So this is my EV, this is EC. So the energy gap is approximately 0.01 electron volt. So here we have 3 electrons. The electrons is majority carriers, 1 or 2 holes will be there. Here the holes will be majority carrier. Okay, so for N-type semiconductors we have a majority of electrons and minority is holes. Here for P-type semiconductors their holes are dominating because each impurity which will provide one holes to the process. So that's why it's called P-type semiconductor because holes are the positively charged. If you have any doubts and if you have any feedback, write in the comment section. I will explain. Okay. So next I'm going to explain the next part. It's called PN junction. This is very important concept here, right? Okay, next is important concept PN junction diode. Actually, we have a P-type material and we have an N-type material. So P-type material is majority of carriers is a positive type material. N-type is the negative type material. P type means your holes is majority and electrons is the minority carriers. For N type material, electrons is majority and holes are the minority carriers. So first I'm going to start with, initially we have a P type and N type. Okay. Here I'm going to write the majority carriers only, right? So the majority here, majority. Here N type majority is electrons. Here P type majority is holes. Okay. There is a electrons are majority carriers, here holes are majority carriers. Because of the concentration gradient, we have a large number of electrons here. So the electrons are diffused from here to here. Here we have a large number of holes. The holes are diffused from here to here. So this is called electron diffusion. This is called hole diffusion. This process because of the concentration gradient. Because of the electrons always flow from high potential to low potential. Here is my holes are majority carriers. Here holes concentration is larger. This moves from high potential to low potential. So this is called diffusion. This is called electron diffusion. This is called hole diffusion. So each electron just moves from here to here. What's happening? So the number of electrons which will leave a positive charge here. If each electron is moves from here to here, it leave a positive ion here. So this is plus, plus, plus. So each electron is moving from here to here, it leave a positive ion here. When each hole is moving from here to here, it left a negative ion here. Okay. So because of this positive charge and because of this negative charge left by these holes and electrons, there will be a layer is formed. This layer is called depletion layer or depletion region. So this is called depletion region or depletion layer. Okay. Okay. Next. So this is because of majority carriers motion. So each electron moves from here to here. There's a potential gets increases. For example, suppose to consider a bowl. Okay. So this is my p-type bowl. Okay, p-type bowl. There is no electrons initially. Approximately, there is no electrons in this side. So I'm going to bring one electron from N to P. There is no opposition. So no problem. Next, I'm going to bring the second electron from P to N to P. What's happening? The second electron moves from here to here. If I put another electron here, what's happening? I have to do work against the first electron's repulsion. Because my first electrons inside the bowl, they will oppose the second electron. I'm doing some work. So what's happening? Initially, there is no potential. Because of the first electron, there will increase in potential. I'm going to bring the third electron from here to here. What's happening? My first two electrons combined together oppose my third electron. So I have to do more work. So my potential again gets increases. If I bring some n number of electrons from here to here, so I have to work against n minus 1 electrons. So if you have some 10 electrons now, if I bring my 11th electron from here to here, what's happening? My 10 electrons combined together oppose the motion of the 11th electron. So I have to work against the 10 electrons. So the work done gets increases. After certain limits, what's happening? The potential will be larger. There is no further flow of electron from N to P. Why? What's happening? Because once the system attains equilibrium, so the number of electrons moves from here to here is equal. For example, here initially we have 100 electrons. Here 0 electrons. If this electrons moves from here to here, 49. If 50 electrons are moved. If the 51st electron starts moving from here to here, what's happening? This will become a low potential. This will become a higher potential because of the electrons which will not move from higher to, which will move from higher to lower potential. So this will become low potential. So there is no further flow of electron from here to here. So this particular potential is called barrier potential. So this is called barrier potential, right? Okay, sir. This is what happening? No. Actually, we have another process. It's called drift. This is because of the minority carriers. So here we have a minority carriers. Here the minority carriers are holes. For p type, the minority carriers are electrons. See, these positive ions is left by these electrons. These negative ions left by these holes. This is because of the majority motion of the majority carriers. What's happening here? The electrons here are the minority carriers. This is attracted by this positive charge, and these electrons are moving from here to here, and this holes is attracted by this negative charge, and these holes are drift from here to here. So this is the motion of the minority carriers. This is called the drift. The current produced, the motion of this electrons is called drift of the electron. The motion of this holes is called drift of the holes. The electrons moves from here to here, the holes moves from here to here. This is because of the motion of the minority carriers. So once the barrier potential attains, here the system, the number of minority carriers equals to the number of majority carriers. Here the number of minority carriers equals to majority carriers. Then the system attains the barrier potential. Once the system attains barrier potential, there is no further flow of electron from N to P and holes from P to N. Okay. Finished. Sir, once the process is stopped, then what we can do? There is no flow of electrons, which means there is no conduction process. There is no flow of holes. There is no conduction process. So how to overcome these difficulties? To overcome these difficulties, we are going to apply the external potential. It's called bias. We are going to apply some biasing. We are going to apply some external potential to overcome this problem. So those things we'll discuss in the next class. So I just stop at this point. If you like this video, share it with your friends and subscribe our channel to get the regular updates. We'll meet in the next class. Thank you.